Chapter 3. Now we get to see the architecture in action. We're going to trace exactly what happens, step by step, when you write data to and read data from an Iceberg table. This is where the theory becomes real. Let's start with the simplest write operation, create table. When you run the command, Iceberg creates an initial metadata file containing the table schema and partition spec. Since the table is empty, there are no data files, manifests, or snapshots with data yet. The catalog is then updated to point to this metadata file. Now when you run an insert, Iceberg first reads the current metadata from the catalog, writes the new Parquet data file, and creates a manifest file containing the file path and write time statistics. It then creates a manifest list representing the new snapshot, followed by a new metadata file with the updated snapshot history. Finally, the catalog pointer is atomically updated to this new metadata file. The key idea is that Iceberg never modifies metadata in place. Now let's talk about merge, which is the upsert operation. This is more complex because it's both a read and a write. The engine first reads existing data to find matching rows. For matches, depending on your configuration, it either rewrites entire data files with the changes applied, that's copy on write, or it writes delete files plus new data files, that's merge on read. For rows that don't match, it simply inserts them as new data files. Then the same metadata dance happens. New manifest files, new manifest list, new metadata file, atomic catalog swap. Now let's flip to the read side. You run a select query, watch how the pruning cascade works. Step 1. The engine asks the catalog for the current metadata file location. Step 2. It reads the metadata file to find the current snapshot and its manifest list. Step 3. It reads the manifest list. If your query has a partition filter, it can skip manifest files whose partition bounds don't overlap. Step 4. It reads the remaining manifest files and checks column-level statistics. If a data file's maximum value for a column is less than your filter's minimum, that file is skipped. Step 5. Only the surviving data files are actually read. Think about what just happened. You might have a table with 10,000 files, but after pruning, you only read 50. That's the power. And time travel. It's beautifully simple. Instead of reading the current snapshot from the metadata file, the engine looks up a historical snapshot by ID or timestamp. Then it follows the exact same pruning path, just starting from an older manifest list. No data duplication needed. The old files are still there, referenced by the old snapshot. Let's test your knowledge. Question 1. What ensures readers always see a consistent table state during concurrent writes? The answer is the catalog's atomic pointer swap. Until a writer atomically updates the catalog pointer from the old metadata file to the new one, all readers see the previous state. After the swap, they see the new state. There's no in-between. Question 2. Why does every write create a new metadata file instead of modifying the existing one? Immutability provides several guarantees. It enables time travel since old metadata files still exist. It ensures consistency since readers always see a complete, valid state. It enables safe concurrent access since no file is ever partially written or corrupted by simultaneous operations. And it creates a natural audit trail of every chain. Question 3. How many levels of pruning occur during a read, and what does each level use? 3 levels. First, manifest list pruning uses partition-level summaries to skip entire manifest files. Second, manifest file pruning uses column-level statistics like min and max values to skip individual data files. Third, within Parquet files, row group statistics allow skipping row groups. Each level dramatically reduces the data that needs to be read. Excellent. That's Chapter 3, the big picture. Writes always create new immutable files and atomically swap a pointer. Reads cascade through the metadata tree, pruning at every level. This combination gives you both safety and speed. Next up, we'll learn how to make your tables even faster with optimization techniques.